So my name is Martin Vuagnoux. I'm coming from the Swiss Federal Institute of Technology in Switzerland, most known auf Deutsch in ETH. I will present you a new method, new fuzzing method, in order to uncover buffer overflows. Normally, I will give all the background to understand things, so the idea is to be just cool, so don't be afraid of the technique. Yeah. So the idea, as you have seen probably yesterday, another guy, Martin Jones, I think, presented new techniques and give a sort of state-of-the-art of the technique used in order to find buffer overflows. But in this case, we never have source code. The idea, in fact, is to test softwares under, for example, Microsoft Windows, but under GNU2. So first, I'm sorry, I will just have to say you what is a buffer overflow. Probably you have listened this kind of information for 1,000 times. Then I will give the state-of-the-art of techniques used to uncover buffer overflows. We will see exactly what is fuzzing. Then I will present you the technique called fuzzing by weighting attacks with markers. I will present you Autodafé, an implementation of this technique. And finally, just two demonstrations. First, a small introduction. I wanted to speak a little bit about Alan Turing. Alan Turing is one of the fathers of the computers. He worked at Bletchley Park, and his story is quite interesting because when he was there, he was with mathematicians, and he was not very well because he said, I'm not very smart, I can't find something very incredible in cryptography, in cryptanalysis. And the director of the Bletchley Park say, okay, you have your own ideas of how to cryptanalyze crypto systems, so try to do on your own way. And that's why he invented the first computer called the bomb to do a simple exhaustive search. But in fact, Alan Turing was, for me, the first references of consequences of a functional error. In a paper, Computing Machinery and Intelligence, published in 1950, he tried to answer to the question, can machines think? And he reduced this problem to a game, the imitation game. So it's a very simple game. Now it's famous due to CAPTCHA. For example, when you create an account on Hotmail, you have a small number, just 12 strange, you have to rewrite it. It's just to make the difference between a human and a script, a computer. It's quite the same game. First, you have a human, an interrogator. Then you have two entities, and for 5 minutes, the interrogators ask questions to A and B. There is one human and one computer. The goal is, after 5 minutes, to know who is the computer. If the computers can answer like a human, you can say machines can think. To do that, the goal of the computer is to influence the decision of the interrogator. It can use human psychology. For example, you give a computation to do, an addition. The computer can just simulate a reflection, a few seconds, and give, why not, a wrong answer. The question is it possible for the interrogator to use something to change the behavior, to influence the decision of a computer? Turing said yes with functional errors. For example, if we have a small processor, 8-bit processor, just recognize bytes, you can ask to add 1 to 2056, and it can answer null, so you can have sort of proof that you are speaking to a computer. But is there another solution to modify the decision of a computer? If we look with the case of a human, you can use senses: hearing, sight, touch, smell, taste. And with them, you can try to convince the human to threat him, to fear, or to torture him, always in order to influence his decisions. With computer, you have inputs, like inputs fields, protocols, files, RPCs, library call, or other stuff. But in fact, you cannot really convince, threat, fear, or torture a computer. They are finite state machines. So there is a solutions, and now the most used is buffer overflows. So what is a buffer overflow? Very small example, few details. There is a simple call, the famous string copy function. This software just asks for an argument, copy it on a buffer of 16 bytes, print it, and exit. A small example, you give a string, and it just prints it like this. Why functions are used? In fact, when a software is trying to do something 1,000 times, especially before, the memory was a big problem. So the solution is to copy the same instruction for 1,000 times in the memory. But the idea is to use a function. A function is only on one part of the memory, and when you need to use this function, you just simply jump on an address, and then you execute the same routine. But what to do when the function is terminated? You need to know how to come back to, in this case, the main function. To do that, you use a part of the memory called stack. And there, you save the return address before jumping on the function. You save another value, not very important. And then you define, in this example, a buffer of 16 bytes. And you see there how the buffer is filled. You start here, and in our example, you just fill like this. So the idea is, if we enter data, much more data than the size of the buffer, you will simply overwrite first the save frame pointer, and finally the return address. And then when the function will exit, you can say to the process to jump in another part of the memory. In this case, it's possible because the function string copy, it doesn't check if the destination buffer, in this case the buffer, is big enough to contain the data of the argument. Here is a proof using GDB, where you launch the same software, the program. You see that at the first case, it's OK. And then you see these bytes overwrite the return address because we receive a signal. In this case, a segmentation fault, because in this address, you cannot execute an instruction. In practice, when you want to take control of a process, the idea is just to jump in a part of the memory you control and where there is what we call a shellcode. For example, give you a backdoor or something else. There is different types of buffer overflows. We have seen here the basics, the school case of stack overflow. You have heap overflow, format string, integer overflow, and other types. So now, basically, the goal is to find buffer overflows in softwares. So how to do it? Let's see how a program is created chronologically. First, we have a source code. It's compiled, and you obtain a binary file. It's executes, and you have this binary mapped on the memory. On each step, you can try to find buffer overflows. The first one is simply to analyze the source code. And then you can try to discover potential flows. A basic example presented yesterday is rats. And in our example, we have the results. First, the definition of a local buffer. And then, the most important, the use of string copy. The advantages of this technique is very fast. You don't need really skills. You can do this job automatically, and it checks completely the software because you have all the source code. But the drawbacks are you need the source code, and it's not always the case. It detects only what we can call basic vulnerabilities. You have a lot of false positives. For example, on SendMail, you have 4,000 reports about just a stack-based buffer. And it's based on the name of the function. I remember it was Samba who was backdoored by, the source was backdoored for 2 days, and he just had a define to change the functions like strncpy, the secure version of string copy, by string copy. Then, if you have just the binary file, you can try to do a static binary analysis. It's quite hard. In this example, it's the same function using a tool called IDA. There, the pros is it's the most in-depth method. You don't need the source code, but you need to know very well assembly. You can detect quite complex vulnerabilities because you have another abstraction, which is a machine language. The drawbacks is you need the binary software, and most important, you need very good human skills, and of course, it takes a lot of times. The third method is to use dynamic binary analysis. In this case, the first things you need is just to simulate an interaction. You need to have something who can use the software. It's what we call a fault injection tool or a fuzzing tool. And then you need a tracer or debugger in order to analyze the reaction of the target software. You have quite some examples. Protos, Fuzz, probably the most known Spike and Pitch. And for the debugger, it's quite always the same GDB. LEDBG. You have Valgrind too, which can be used, or Ltraces, strace. The fault injection is not really new. You can find this technique in order to test hardware, for example, even cars. The idea is just to do some basic changes, like a bit flip, and to analyze the reaction of the software. The goal is not security related, it's to detect bugs in general. And most of the case, the bug is detected because the software crash or you have the memory, a full memory state. So what is the fuzzing? The fuzzing is, at least for me, a subset of fault injection because it was designed, it was invented to uncover security-related bugs. Fuzzing comes from the name of the first fuzzer called Fuzz, who was just a software which create random strings and send them to other programs. Let's see what the advantages and the drawbacks in practice. Okay, a small example. It's a very basic protocol. You have first a fixed string, quests. Then you have a length, which corresponds to the length of the variable string. This length is on 32 bits, big endian. And finally, you have a fixed string end. If you want to try to fuzz a server, for example, which use this protocol, you use a fuzzer, and you have the server on a target. If you send random characters, or just A's, in this case, most of the time you have check functions. In this case, the function will, for example, check if the first 4 bytes are equals to quest. Otherwise, the packet is rejected. So it's quite useless to do that. You are wasting your time. If you know that it starts with quests and end with the string end, another check function check if the length of the string is equal to the length value. Otherwise, the package is rejected. Trying to test the strings is completely useless. If you know exactly how is the protocol, you have chances to reach vulnerable functions. This case is inspired by a remote administration software, and the flow still exists. I like to speak with cryptographic problems. So in this case, if you have only 15 bytes, trying all the solutions is like trying an exhaustive search on a key of 120 bytes. If you know how the protocol works, it's only 4 billion solutions to try, only. So the advantages of this technique is you don't need the source code. Sometimes you even don't need the binary. Every uncovered buffer overflows are real. You don't really need skills to do that. You can let the computer doing the work at night. The drawbacks are a lot of tests are useless. And as the binary file analysis, it takes a lot of times. And of course, it's not a total solution to discover every buffer overflows. So a proposition to increase the efficiency of this technique is to reduce the test space. To do that, we have seen through the example that if you understand the protocol, it's much more better. If you especially can parse length, it's better again. And finally, every substituted strings are not relevant. First, understand protocol. In this case, if you know that the protocol is written like this, you can reduce significantly the test space. If you can parse length, it's very important. In this case, the length value should correspond to the length of the string value. And finally, testing some strings are useless. For example, if you test these strings and again these strings, there is chances that it will give the same answer. So if you can reduce the size of the fuzzing library, it's much more better. But these techniques represent the state of the art of fuzzings. The problem is in practice, the size of the test space is still near infinite. So the idea is to reduce it again. This solution, called fuzzing by weighting attacks, has the same objective. So what is the size of the test space? First, we have what we call a fuzzing string library. It's in fact a space which contains all the substituted strings you will test. For example, a lot of A's, a lot of B, etc. Then you multiply the cardinality of this space with the number of strings you want to fuzz. In our example, it's quite simple because we have only one string to fuzz, but in most of the cases, you have a multiple choice of strings. Then you can add another space which corresponds to the number. Fuzzing number is quite important too. So this equation represents the size of the test space. If we want to reduce this size, we know that we cannot really try to reduce the fuzzing string library because normally every field in this library has been chosen because one time a buffer overflow has been discovered by these kind of things. Remember format strings, trying these kind of things. The same thing for the fuzzing number library, but this one and this one can be reduced. And it's a multiplication here, L times S. So it's much, much better to reduce these two subspace. How to do that? For example, by using weights, weighting the attacks. We have a fuzzer and a target. This target is monitored by a tracer debugger. In this case, imagine you send an original packet dumped with a sniffer or whatever. If this tracer is able to say, no, don't fuzz this packet, it's useless to try this one, at least at the beginning. He sends another packet, and then the tracer say, okay, I found something interesting, like a format string, try to fuzz it. Then the fuzzer will try every entries of the fuzzing library and eventually find something. That's what I said. We reduce these two spaces. Okay, it's fine in theory, but how to know if it's relevant to fuzz or not to fuzz a string or a value? Using markers can be a solution. So the question is, what is a marker? In this case, a marker is a string, like this one, and this one. As we have seen, this one can be relevant to fuzz, but not this one and this one, because they are fixed string just used by the protocol. The idea is quite simple. The tracer first say, okay. The fuzzer say, okay, here is the string I want to try to fuzz. He sends a normal request. Then the debugger can analyze how the target software works. And he can say, okay, what I have seen, this string is used by strcpy, so it's relevant to try this string at the beginning. Then the fuzzer knows which string he has to try first, and in this case, find a buffer overflow. So there is 4 steps. The first one, understand known and, why not, unknown protocols. Length parsing, fuzzing, using a fuzzing library, and finally, weighting attacks with markers. Autodafé is an implementation, practical implementation of this technique in order to prove the efficiency. Autodafé comes from his act of faith. In fact, it was used during the Inquisition, especially in Spain. The idea was to burn somebody, and if the smoke is white, it was good, and if it was black, it was not good. But it's too late. So the idea is to torture software, so that's why the name is choose like that. Autodafé is used by 4 modules: ADC, PDML2AD, Autodafé, and ADBG. The first one is to answer to the question, understand known and unknown protocols. It uses a block-based script language. In fact, it's very close to the block-based script invented by Dave Aitel through the fuzzer spike. Here you have a parser which can check your syntax. It's much more for development. It can check your syntax and be sure that your file is correctly done and there is no error. Here is an example of the description of the example. Remember, it's this string. You have quest, a number, a string, and another string. So you define first a packet, a block. This block starts here and stopped here. First, you have a string, fixed string. Then you define a value, size value. In this case, big endian 32 bits. And you give the name of the block. Then, if you change this value or any value on the block, the size will be recomputed and accepted by the check functions. Then there is another string, this one. And finally, the string end. And at the end, you have just a carriage U-turn. You finish the block here, and you send it. By default, it's sent by TCP. The biggest problem if you have used fuzzers like Spike is to write your own script and try to understand how protocols works. So the idea is to use the ethereal engine to recognize 530 protocols. To do that, you just need to export a dump using the PDML function, and then convert this file using this tool. This, you can just dump a SendMail connection, SMTP connection, for example, and after that, just choose what you want to try to fuzz, which field you want to try to fuzz. This is an example of the automated recognition on our SSH communication. The first packet, you see you have some commands, the string, and the order if it's a received packet or a sent packet. For the fuzzing library, the idea is quite simple. You have a file, and on this file, every file describes other files. On every file, you have the letter you want to substitute to every strings. The idea is to test server-side and client-side, because in practice, most of the time, every server are well tested, but clients not all the time. For example, CVS or Subversion are not very well protected on the client side. You can fuzz files. Now it's quite well used, but the idea is to not create connections, but create a lot of files and test each file recursively. The fuzzer, called Autodafé, this is this part here, can be connected to a debugger in order to wait attacks. As I said, the fuzzer can automatically recompute the length fields of each first packet. Here is an example of the size you can give: 32-bit, little, big endian, 16-bit, 8-bit, or even strings using characters. For example, when you send an information using HTTP post, you need to write the content length field with characters. ADBG is in fact a debugger. It's connected to the engine fuzzer Autodafé, and they work together. They communicate using a TCP connection. This software exists on Windows and Unix. The idea is the fuzzer sends first the marker to the debugger, then the fuzzer will send an original traffic in order to analyze the behavior of the target software. Finally, the debugger tracer will listen on every vulnerable function and send reports to the fuzzer and give weights which one he has to try first. To conclusion, what I wanted to say is about Alan Turing. He said that it's not possible in this paper because he considered these machines as mathematical abstracts, fictions. But in practice, this difference can be used by people to change the behavior of a computer. There is a small story about the Apple logo and Alan Turing. I've read on the booklet of the 223 that Steve Jobs said that the logo comes because he was working in an Apple company who sell apples. Another story is to say this is a tribute to Alan Turing, because even if he's, for me at least, the creator of computers, he was rejected by the English community because he was homosexual, and he committed suicide 50 years ago by eating an apple he laced with cyanide. So you can see the homosexual flag with 6 colors and an apple half eaten. Before the question, I will show you 2 examples. One with it's just a school case. It's the same protocol we have seen. And another example, a real case on files. So the first one will use a TCP connection. We'll use the same protocol we have seen. There is a, it's not easy. The first file is what is sent by the ethereal software. It's not clear, and in this case is a sort of ASCII protocol, so even if this protocol is not recognized by ethereal, we can describe it using Autodafé scripts. So with this file, you use the converter PDML to AD, and you obtain this file. As you have seen, it's quite simple. You have a block here and here. This block, first you have a string, fixed string. You have the size, big endian 32 bits of the block. We have another block. I don't know why, I don't remember why. And there you have a string we won't try to fuzz, so you just add fuzz before the word string. Then you have the string end and the return carriage. And finally, you have to send this packet. Then first, in this case, the tracer debugger has recognized these functions and just wait for a connection from the fuzzer. The fuzzer, by using the description of the file, will try to fuzz the field hello 22cc, 22c3. Okay, first the library is loaded. You can see the markers here, and in a few seconds, the fuzzer will try recursively to send much more packets. You see the normal packet, and after that, this field is changed, and the value here, which is the size, is incremented automatically. So as you have seen here, we didn't need to try to test, for example, the field, the string, and our quest, because it was useless thanks to the debugger. And in this case, we have a segmentation fault. Unfortunately, I can't give you the real example. As I said, it's a remote administration software, but it's sort of simulations of the real bug. For the second one, it's a real one, based on file. In this case, it's ghost view. Ghost view has a lot of vulnerabilities, even in the version distributed by distributions. In this case, mine is Slackware, and ghost view is always vulnerable. The first idea is to create a PS file. Here we go, normal PS file, and then we convert it, so it's done by scripts in an AD file. Here you have the version using Autodafé script, and you can find the field we want to try to fuzz. There. Doesn't work, so when you see first string, this string will try to fuzz. To do that, there is no connection. We are trying to fuzz a file, so the idea is we will create 4,000 different files, and a script will try to charge to load every files recursively. So you see there the creations of different files, where every fuzzing variable are changed according to the fuzzing library, or the eggs value library. So the version of Vuagnoux is the last one, if I didn't make mistake, yeah. So now, what we'll do is try to load every file generated and monitor it by the debugger in order to have a state of the failure. You can see the call, and finally, we have a segmentation fault, very basic stack overflow on a Vuagnoux document. I can show you. I can show you something else. The idea is just to count how many markers are used by vulnerable functions. Always in the case of Vuagnoux. So it will load Vuagnoux, as you recognize, and finally give the number of vulnerable calls. It's 170. In fact, there is only 12 vulnerable calls, but 170 markers are called by these vulnerable functions. I had another example, but I can't show you, unfortunately, because as you know now, publication is quite a problem, especially in Switzerland, where there is a law. You cannot give freely exploit or things like that. There is an act. But what I can say publicly is, after testing in many software, especially on the world of Windows, 865 buffer overflows were found. Buffer overflow where you can have access, where buffer overflow you can use, really. Most of the case, heap or stack overflows. So now this tool will be released at the end of the month of January. The idea is to have a sort of framework where you can yourself try to find new flaw or try to audit your own code in practice with fuzzing. So if you have a question or comments. Okay, if it's not clear, I'm writing a big tutorial, so you will find it on the SourceForge at the end of the month of January, and I hope you will use it. Thank you.